This video lecture we will explain about some extension on the least square problem in a way that we will put some penalty term in the least square objective, and that penalty functions are related to several kinds of norm. So this is a problem that is called regularized least squares. So we're going to start with the L2 norm regularization, okay, or we call it L2 regularized least squares. So the problem statement is the following. You minimize the least square objective, but you add a penalty term. You add another term that is the 2 norm of the vector x. And you have allowed to have some parameter gamma that is non-negative. Okay. When you have when you have a when you have an optimization problem that the objective is split into two terms, f1 and f2, if you have put penalty parameter gamma on, like, it's a relative weight, right, between these two objectives. If you put gamma on f2 and if you set gamma to be bigger than 1 and is high, what it means is that you penalize more on F2 objective, which means you want F2 to be less in relative to F1. Okay, so with that concept, it means that when you have added this term, these 2 norm in the x, the 2 norm of a vector represent the size, the magnitude, right? So basically you want the vector x to have a small size, and you can play with that degree of the small size of x by adjusting gamma. As gamma is larger, the smaller norm of x is. Okay. So why do we want x has a small norm? Because remember that after we solve the problem, we get x. The prediction, the estimate of your model, of your linear model, would be a times x hat, right? X hat is the solution that returned from this optimization. So if x hat has a small norm, it means that in the scenario that your A has some uncertainty, if A has some perturbation, your solution will be less sensitive. Your prediction of y, your estimation of y will be less sensitive to the uncertainty in A because your vector x has a small norm. All right, that's the motivation why we are interested in the L2 regularized least squares. This problem has another name too in literature. It's called Tikhonov least square, or the ridge regression, or the L2 norm least square. All right. It is a very simple example. Napat, can you turn off the mic? It is a simple example to arrange that this is the sum of the 2 norm square. It can be arranged into a single one. All right, it can be arranged into a single one like this. And after you take the zero gradient, because it's an unconstrained problem, take the zero gradient and solve for the solution, you will see that the ridge regression has a closed form, has an analytical solution. Okay. Compared to the least square one, the least square. Okay, now you have 2 norm penalty. The extra term here is plus gamma I. All right. So this is also has a nice property that because the matrix before the inverse, when you do the inverse, this matrix is always non-negative, right? But your gamma is positive. So when you have positive semi-definite and positive definite, the sum is always positive definite. which means this matrix is always invertible. If you put some small positive gamma. So regression has a nice property in this sense because you don't have to put any conditions on the rank of A. Just unlike the least square, right? The least square, this expression is valid when A is full rank. We can, as we see more when we talk about maximum a posteriori estimation, or in short a map estimation. This is one statistical method, right? We will see the connection between Tikhonov and map estimation when you use a log prior of Gaussian. Next, the second one. Let me skip to this problem statement. If you have added one norm in the cost objective, right, instead of two norms, this is called L1-regularized least square. I would like to maybe go back to some basic, all right, some motivation of why do we use L1 norm in the least square objective. Now we're going to start with a scalar problem. Suppose you have a objective that is obviously square, and or without the absolute term. Okay, if you just take a look at this yellow term, what is the minimum of f? What is like when A is given? When you minimize f, what is the solution? Toto? Toto, are you here?
Yes. What is the question, Achan? I'm sorry.
The question is the function in the red box, okay, just parabola, center at A. If you minimize this function, what is the optimal solution? X?
Equal to A.
Yes, obviously, A equals to A, right? Okay, now we change a little bit. We add the absolute value of X. All right, this is scalar. All right. How do we do it? Okay, let's say we all know that the absolute value of x can be split into two terms. What are those two cases, Sitipat? The absolute value of x equals to
x and
wait.
x
Yes, is equal to x when
x is non-negative.
Right, and of course equals to minus x when x is negative, right? Okay, so I'm just considering those two cases. So the first case is x is non-negative, right? Then my fx is going to be 1/2 x minus a squared plus gamma x. All right. Then I will just complete the square. Nothing fancy, right? This is a square function plus linear. You can just recomplete the square, and I get this. I end up with this. All right. Then you will see that, okay, in that case, if I minimize it, the minimum would occur when x is a minus gamma. All right. But because I put the condition that x must be non-negative, okay, so the condition is given by the yellow term, provided that a must be bigger than gamma to make my x star non-negative, just like I assumed. Okay, so when I do the same, when x is less than 0, my fx is of course here it would be minus gamma x, right? And then I complete the square again. When I see this expression, I would say, okay, my x star would be a plus gamma. And of course, provided that my x star has to be negative, right? So my a must be less than minus gamma. You can easily also verify that Also, now, so it's like you have two cases, right? It's when A is bigger than gamma, when A is less than gamma, all right? Your X star is A minus gamma, your X star is A plus gamma. You can also show, I mean, it's not hard to verify that when the absolute of A is less than gamma, which is a yellow area, your X star must be 0. Okay. So with that 3 conclusions, okay, we can write in a compact form that your solution, whenever A is bigger than whenever your absolute value of A is bigger than gamma, which is the blue term, the solution is given by this, the blue term. And when A is magnitude of A is less than gamma is 0. Okay. Okay. So with this conclusion, it means that remember that your A is a problem parameter. The gamma is also a problem parameter. So whenever the magnitude of A is less than gamma, you get the 0 solution. So it means that, oh, if your gamma is big, right? Your gamma is very big, so it's not hard to satisfy these condition. It's going to be easy for A to be less than gamma when gamma is really big. So the interpretation is that, so this is the simplest case of L1 regularization, because again, L1 norm is what? The sum of absolute value, right? So this is like the L1 penalty. By allowing the gamma to be big enough, you can make your solution 0. Of course, if we extend to the vector case, okay, remember that the 2 norm and the 1 norm, if you put it into the sum, it's going to be this, right? It's going to be sum of xi minus ai squared plus absolute value of xi. All right, so we can just exploit these result on the scalar, because I mean what you see here is a sum of if the sum of several terms. So the optimal solution of this problem can be extended to the vector case as the following. Whenever the vector A, you know, has the magnitude of less than gamma, which means this is the vector notation. It means that like I put a very notation in the element-wise fashion. So whenever AI less than gamma, xi will be 0. Okay. Okay. And whenever magnitude of AI is bigger than gamma, your xi is going to be magnitude of AI minus gamma sine. This is the sine function. Sine function is the what? What is the sine function again? The sine of x is what? Is 1 when x is positive, is minus 1 when x is negative. So when x is 0, you can assign it, it's up to you, you can assign it to 0 or you know, either one of these two cases. Okay, with this conclusion again, let me emphasize that, so whenever gamma is big, if gamma is big enough, some of the entries in A will be less than gamma, which means some of the entries in X will be 0. So whenever the vector x is 0, okay, we say that if x has a lot of zeros in the vector, we say that x is sparse. Okay, and sparsity in the vector x is in some application is a desirable property because it means that you use less number of parameters, right? So instead of having n non-zero entries, what you can do is you just have like r non-zero entries, so it's gonna be like more compact in terms of storage, in terms of like using x as a model parameter. We say that, oh, that model has less number of parameter, that model is less simple. That's why the motivation that when you add L1 penalty into some cost objective, is gonna introduce 0 in the solution. So that is one feature, that is a significant feature of L1 norm penalty. That is why we add L1 norm in the least square objective. So it is a convex and heuristic method to find a sparse x that ax is approximately y. So again, when you have a sum of two objectives, right, it means that you balance between these two criterions by playing with the penalty parameter gamma. If gamma is less and less, which means that you care more about the quadratic loss here, it means that you want your x to like approximate y very, very well relative to the L1 norm of x. But if you put gamma to be very, very big, it means that I focus more, I want to penalize more on the one norm of x. In that case, my x will be very, very sparse. Okay, if the L1 norm of x is less, right, because you put more penalty on gamma. When x is sparse, of course, you gain this objective that, okay, my x is going to be, oh, very, very compact representation. I'm going to use like a smaller number of parameters, but then at the same time, you have trade that the cost objective, I mean, like what you intend to use this x to approximate y, like ax to approximate y, is going to introduce large error, right? Because now you use sparse x. So let me, so that you're not confused, when gamma is big, right, this term is going to be less, but this term is going to be higher. Okay, so it's kind of, you need to trade off by choosing an appropriate gamma. I say this is a convex heuristic because, again, as we have seen the lecture, the yellow term is a convex function. The blue term is a one norm. Any kind of norm is convex. So the whole problem is convex. In the literature, this problem is called a lasso problem or basis pursuit. It is non-differentiable problem because of the L1 norm term. Why it is called non-differentiable? Because the L1 norm has a basis from the fact that it is a sum of what? It is a sum of this is a sum of magnitude in xk. And because you know that the magnitude, right, the absolute value, this function, the absolute value of x, it is non-differentiable at 0. Because f of x, when x is negative, right, the slope is -1. The derivative, which is the red line, when x is positive, the derivative is 1. But at 0, the derivative is not defined. So that's why this function I mean, it's differentiable at every point except x is 0. These L1 regularized least square unfortunately doesn't have a closed form solution, just like doesn't have a closed form solution like least like regression or the least square. So that's why we need numerical method to solve it. And again, as we will see when we talk about a maximum, a posteriori or map estimation, we will see that this can be interpreted that is a map with the log prior as of Laplacian. Okay, now let me illustrate the results. All right, so I'm going to use A and B, 100 measurements, 500 variables. My x is a vector of 500. I use gamma 0.2. All right, I solve regression. I solve L1 norm least square, and then so I'm gonna get x, right, get as a solution. My x has a 500 entries, so I just plot the histogram of my x star. So first take a look at the histogram. For L2, you see that the histogram of x is kind of widely spread, right, in the range of -1 or minus 0.1 to 0.1. But for L1, you see that most of the entries are concentrated at 0, which means there's bunch of like a big portions of x are 0. So x star is sparse when it is a solution of L1 regularized problem. If we now in this graph, x has 500 entries, right? So in this bottom graph, I run the problem again, but I use the case that my n is 5, so my x has 5 entries. So I solve the problem where I vary gamma from 0 to 40. Okay, as you will see, again, when I use less gamma, what do I have? If I use small gamma, my L1 norm is big, right? Why my L1 norm is big? Because most of my x will be non-zero. But when gamma is big, my L1 norm of x is going to be less and less, which means x is going to be sparser. In this case, when gamma is small, my x is dense. Dense means a lot of x are non-zero. So with that observation, I plot the solution path. This is the value of x1 x5, okay, as gamma varies. You will see that, okay, let's take a look at the lasso case. You will see that for certain gamma, okay, some entry of my x becomes exactly 0. Okay, here let's see, x1, x2, x3, x4, and x5, right? So when gamma is around point something, my x4 and x3 are exactly 0. As I increase gamma, now x2 becomes 0, right? And but when gamma is 4 something, all of my x are 0. Completely sparse, 0 solution. Okay. While we see the rich or the Tikhonov solution, we see that as you increase gamma, you see that the entries of x, they become smaller and smaller, but they are not exactly 0. Like they're just tails of small values. Okay, so this is different, the two main different behaviors of L1 and L2 norm regularized least square. Okay, you will see that in the literature, the L1 regularization problem can be cast in different representations. Instead of having L1 norm as a cost objective, some people also put it in as a constraint. So this is to say, I want to minimize the two norm, the least square objective, subject to the one norm of my x must be less than t, where t must be given by the user. The meaning is always the same, right? So you are the one who decide about the degree of the sparsity in X. Okay. The problem 1 and the problem 8, I mean, they are not exactly equivalent, but using some, I mean, they can produce the same behavior of the solution. We say that this is the Lagrangian representation of the problem 1. Okay. So that would be all for the least square regularization. Regularized least square problems.